What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles and water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithionphosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyllite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off. and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santacilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glass-making equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo-American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, like 60 tons of platinum, comes primarily from recycling auto catalyst and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes. Every year, shipyards launch massive icebreakers and cruise liners, vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts, that's more than 30,000 horsepower, and dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of 2 fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers had been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution: move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work. It worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer. And after that, the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year.
Each year, the world burns energy equivalent to the power of thousands of volcanoes. And all of this is contained thanks to a material almost no one thinks about: refractory brick. Its market exceeds 30 billion euros, and more than 70% of this mass is consumed by a single industry: metallurgy. Just to line one blast furnace requires up to 4,000 tons of such brick. How does ordinary clay transform into stone capable of withstanding over 1,600 degrees? And why, without this material, would factories, plants, and even our fireplaces grind to a halt? Watch carefully. Everything will become clear. At the heart of it all lies not ordinary red clay, but a particular variety, refractory clay, or kaolin. Its uniqueness derives from its chemical composition, dominated by two oxides, aluminum oxide and silicon dioxide. It is precisely their elevated content that endows the raw material with its principal characteristic, an extraordinarily high melting point. To impart stability to the finished product, manufacturers employ a rather cunning technical stratagem. A portion of the extracted clay is not sent directly into production, but is first fired in kilns at temperatures reaching up to 1,500 degrees. Through this process, the clay loses its plasticity and transforms into an exceedingly hard, stone-like material known as shamat.
This prepared shamat is then crushed and used as the principal component, with a specified quantity of fresh plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces shrinkage of the products during final drying and firing, preventing warping and cracking. So, the process begins with the preparation of components. Extracted clay and pre-prepared shamat are fed to the grinding line. Giant crusher jaws split the large pieces, and then roller mills and ball mills relentlessly grind them down to a fine powder with a precisely defined grain size.
Following crushing, automated dosing systems weigh each component: grog powder, clay powder, water, with computerized precision according to the formula. This entire mixture is sent to powerful mixers, where it's intensively blended until an absolutely homogeneous mass, known as the batch, forms. Next, the shapeless mass must acquire its contours. The most common method is semi-dry pressing. The batch, containing minimal moisture, is loaded into high-strength metal molds. Then, a press bears down upon it with tremendous force, measured in hundreds of tons. Thanks to this colossal pressure, what emerges is a dense, smooth block with perfect geometry, a green brick. The next stage requires not strength, but patience and precision. The raw brick is carefully arranged on trolleys and dispatched to long tunnel dryers. This is a slow and delicate phase, which can last from 1 to several days. Inside the dryer, a meticulously controlled microclimate is maintained. Temperature gradually rises whilst humidity decreases. It is essential that moisture escapes from the brick as uniformly as possible. Any haste will result in the outer layers drying faster than the inner ones, which creates critical stresses and simply tears the brick apart with cracks from within. When all the water has been removed, the culmination arrives: firing. The brick enters the fiery tunnel of the kiln, where it awaits a true transformation. Moving slowly through different zones, it gradually heats to peak temperatures, which for fireclay brick reach 1,400 degrees, whilst for high alumina varieties may exceed 1,750 degrees. This is not merely drying, but a profound metamorphosis. At such temperatures, mineral particles soften and sinter together, forming a robust ceramic structure. Within the system of aluminum oxide and silicon dioxide, new crystalline compounds form, particularly needle-like mullite crystals, which, rather like reinforcement bars, permeate the entire structure of the brick, imparting exceptional strength to it. Having passed the peak heating stage, the brick moves just as slowly through the cooling zone. This phase is no less crucial, since rapid cooling would cause thermal shock and destroy the product. What emerges from the kiln is an entirely new entity, a hard, resonant, slightly rough-textured block that fears no fire. What follows is purely quality control. Each piece undergoes rigorous inspection for dimensional accuracy and absence of defects, after which it is marked, packaged, and dispatched to fulfill its principal purpose, to contain flame. To grasp the true significance of refractory brick, one need only consider the numbers. The global refractory materials market represents an industry valued at more than 30 billion euros annually, and over 70% of this colossal volume of product is consumed by a single sector, ferrous metallurgy. The internal protective lining of one large blast furnace alone may require between 2,000 and 4,000 tons of refractories. And a single steel pouring ladle, which transports hundreds of tons of molten metal, gets through several complete sets of lining per year. The standard fire clay brick, grade Sha A, which is the most common type, weighs approximately 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. Refractory brick lines the interiors of blast furnaces, where pig iron is born from ore. It provides refractory lining for oxygen converters and electric arc furnaces, in which pig iron is transformed into steel. Enormous steel pouring ladles transporting molten metal are likewise protected internally by armor of refractories. Moreover, for each zone of the unit, a particular, specific type of brick is selected. The second most significant consumer is the cement industry. Long rotating kilns, several hundred meters in length, in which cement clinker is fired at temperatures of 1,450 degrees, are entirely lined internally with specialized varieties of refractory brick. The glass industry also cannot exist without refractories. Enormous tank furnaces, where glass mass is melted at temperatures of approximately 1,600 degrees, are lined with special, highly resistant types of brick, which are capable of withstanding for years not only the heat, but also the aggressive chemical action of molten glass. Besides these giants, refractory brick is used in thermal power engineering for lining boilers, in the chemical industry for lining reactors, and also in waste incineration furnaces. And, of course, on a far smaller scale, we encounter it in everyday life. It is precisely from Shamat brick that fireplaces, stoves, and chimneys are built, because it guarantees safety and longevity.
Imagine a material born from sand and stone, fired at temperatures exceeding 2,000 degrees Fahrenheit, stretched into threads thinner than a human hair, then transformed into either building insulation, boat components, pipes, composite beams, turbine blades, or even heavy-duty industrial structures. This is fiberglass, one of the most underestimated materials in modern industry. At first glance, it seems ordinary. Insulation here, composites there, holes and panels everywhere. But beneath this ordinariness lies an incredibly powerful technology. Because fiberglass isn't just melted glass pulled into threads. It's a meticulously calibrated industrial process where chemical composition, melting temperature, drawing speed, protective coating properties, and subsequent processing methods determine whether the material becomes brittle garbage or the foundation for strong, lightweight engineered products. And today, we're breaking down how fiberglass is manufactured for industry, why it's simultaneously light and strong, what forms it takes, and how one of the most versatile materials in modern engineering is born from molten glass. Everything starts with raw materials, and here's one of fiberglass's biggest paradoxes. The base is incredibly simple: silica sand, limestone, soda ash, and a few mineral additives. But it's the combination of these ingredients that determines the fiber's future properties. Pure quartz alone needs extremely high melting temperatures, so manufacturers add substances to control the process and change the final product's characteristics. Additives can boost chemical resistance, improve electrical properties, increase strength, or tailor the material for composites and insulation. Industry uses different types of glass. Some work best for general applications, others for chemically aggressive environments, still others for higher mechanical strength. So, fiberglass production doesn't just start with dumping sand into a furnace. It starts with precise formulation. At this stage, the material still looks like ordinary mineral mix, but this is where its future role gets locked in. Whether it'll be cheap insulation, reinforcing fabric, or the foundation for complex composite structures. The next stage is melting. The prepared mixture gets sent into massive furnaces, where at temperatures around 2,500 to 2,550 degrees Fahrenheit, sometimes even higher, the raw materials transform into a uniform glass mass. Pure quartz requires even higher temps. But the key part of this stage isn't just the heating itself, it's controlling the state of the melt. The furnace is divided into zones so the material doesn't just melt, it purges bubbles, becomes uniform in composition, and hits the exact viscosity needed. If the melt is unstable, if impurities or air pockets remain, the future fibers will have weak spots. And in a material that needs to be both thin and strong, even microscopic defects are critical. Essentially, at this stage, the plant isn't just creating liquid glass. It's creating a high-precision industrial melt that has to behave perfectly in the next phase. Because what comes next isn't pouring it into a mold, it's turning it into threads. And for that, the glass needs nearly jeweler-grade precision in temperature and flow. The most impressive stage? Turning molten glass into filaments. Liquid glass flows to special spinnerets. The industry calls them bushings. These are plates made from an expensive, incredibly resilient alloy of platinum and rhodium. The glass passes through hundreds, sometimes thousands, of microscopic holes. From each hole emerges a hair-thin stream of white-hot material. But that stream isn't fiber yet. Real fiber is born in the drawing process. High-speed mechanisms literally yank the glass downward at tremendous velocity, and that force transforms the molten mass into ultra-fine continuous filaments. We're talking diameters measured in micrometers, several times thinner than a human hair. It's the drawing speed and rapid cooling that prevent the glass from crystallizing like ordinary, brittle material. Instead, you get an amorphous glass filament with engineered properties. And here's where you really see it. Fiberglass isn't just molten glass, it's a material born at the intersection of fire, velocity, and precision mechanics. But just pulling the fiber isn't enough. Glass by itself is brittle, and if you leave fresh filaments unprotected, they'll start getting damaged, rubbing against each other, and quickly losing their properties. So almost immediately after drawing, the fibers get a special chemical coating, sizing. This is one of the most underrated yet crucial elements of the entire technology. This coating doesn't just reduce friction and protect the fibers from breaking during winding, it also preps them for their future work in composites, improving the bond between smooth glass and the resin that'll later hold the fibers together in the finished product. The right sizing determines how well the fiberglass will interact with polyester, epoxy, or other matrices. In other words, this is where it's decided whether the glass strand becomes just a bundle of brittle fibers or a full-fledged reinforcing material capable of performing in real-world structures. Sometimes it seems like fiberglass strength is all about the glass itself, but in reality, much of it comes down to the chemistry of its surface. Next comes the transformation of fibers into semi-finished products. Threads are gathered into strands, rovings, wound onto spools, chopped into short fragments, formed into mats, fabrics, or specialized directional reinforcement structures. And this is where fiberglass splits into two major application worlds. The first is insulation. Here, the fibers are made more random, turned into a bulky mat, bound with special compounds, and you get a material that traps air incredibly well, which means it traps heat and sound. The second world is composites. Here, the glass fibers don't just sit in a loose layer. They become a reinforcing framework for resins. These combinations produce boat hulls, panels, pipes, profiles, tanks, industrial flooring, and countless other products. Some applications use woven roving, others use chop strand mat. Still others use directional knitted structures where fibers are oriented for specific loads. In other words, fiberglass isn't one product. It's a family of industrial forms that starts with the same thread, but ends with wildly different application technologies. The story of fiberglass and industrial profiles is especially fascinating. When glass fiber meets resin, it stops being just a bundle of threads. It transforms into a composite where each material handles its own job. Resin handles compression beautifully, locks in shape, and spreads the load. Glass fibers excel at tension. It's roughly the same logic as reinforced concrete, where concrete and steel rebar compensate for each other's weaknesses. This combination makes fiberglass light, strong, corrosion-resistant, and easy to mold into all kinds of shapes. One of the most important industrial methods is pultrusion. Fibers get pulled through resin and a heated die, producing continuous profiles with constant cross-sections. That's how you make beams, angles, tubes, sheets, grating, and other elements that work where metal is too heavy, rusts, or fails on electrical and thermal properties. That's where the power of fiberglass hides. It lets you create structural materials from what seems like an incredibly fragile starting point. So why is fiberglass both lightweight and strong? The secret's in the scale and structure. The thinner the glass fiber and the fewer defects on its surface, the higher its mechanical strength. And when lots of these fibers combine into a smart shape and work together with resin, you get a material with an incredibly high strength-to-weight ratio. That's exactly why fiberglass and fiberglass-based composites are so widely used in transportation, construction, energy, and manufacturing. It doesn't replace metal absolutely everywhere, but it works beautifully where you need a combination of low weight, corrosion resistance, electrical insulation, and solid mechanical durability. Plus, fiberglass can be adapted for different tasks by changing the glass composition, fiber type, reinforcement direction, and matrix properties. That's how you end up with a material that can be a soft insulation blanket, a rigid composite beam, or part of a complex industrial system. And all of it, from sand, minerals, heat, and incredibly precise technology.
Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius. And a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways.
The cylinder block of a freight locomotive weighs 50 tons, 4 meters long, 2 meters wide, 5 feet tall. It's a single cast iron casting, 16 cylinders, 11 inches in diameter. An engine producing 4,500 horsepower, pulls a 5,000-ton train through the Colorado mountains and Nevada deserts without stopping. How do you cast the heart of such a monster? Today, you'll see the complete cycle at the Wabtec plant in Pennsylvania, from molding sand to a block with tolerances measured in micrometers. If you want to see how they make the engine that moves America, subscribe to the channel. Here, we show the manufacturing that keeps the world running. Molding sand. Silica sand, grain size 0.08 to 0.16 inches, 50 to 70 grit on the AFS scale. Mix with phenol formaldehyde resin, resin at 3% of sand weight. Add hardener, sulfuric acid ester, at 0.5% concentration. The resin binds the grains. When cured, forms a structure with compressive strength of 435 pounds per square inch. The mold must withstand contact with molten cast iron at 2,460 degrees Fahrenheit. If it cracks, 33,000 pounds of metal spills onto the floor. Mix in edge runners. Time, 8 minutes. Moisture content of finished mix, 4%. Temperature, 72 degrees. Mix is ready. They make the mold in a pit measuring 16 feet by 10 feet by 6.5 feet deep. They lay the mixture in layers of 8 inches. They compact it with a pneumatic tamper. Air pressure 90 pounds per square inch, 300 blows per minute. Density of the compacted sand 100 pounds per cubic foot. They install the cores. Cores are sand inserts that form the cavities, oil channels, water jackets, piston chambers. 120 cores per block, each one made separately. Sand with quick hardening resin blown into the tooling at 115 pounds per square inch. The resin hardens in 30 seconds. They extract the core, check it with calipers, tolerance plus or minus 1/25 of an inch. They install them in the mold per the drawing. Installation accuracy plus or minus 1/12 of an inch. An incorrectly installed core creates a defect, shows up after machining, or in operation. They close the mold with the upper half, secured by 24 clamps, 10 tons of clamping force each. The mold is ready for pouring. They melt cast iron in an induction furnace with a 20-ton capacity. They load pig iron grade SCH25, carbon 3.4%, silicon 2.2, manganese 0.8, sulfur 0.12, phosphorus 0.2. They add alloying elements. Nickel 1% for strength, chromium 0.5 for hardness, molybdenum 0.3 for heat resistance. Furnace power 3 megawatts. Melting time 2 hours. Melting point 2,190 degrees Fahrenheit. They superheat to 2,462. They take a sample, analyze it with a spectrometer. Carbon plus or minus 0.1%. Silicon plus or minus 0.15. Composition confirmed. They begin pouring. The metal pours into a ladle that holds 18 tons. The ladle's lined with fire brick, 8 inches thick. Withstands temperatures of 2,700 degrees. A crane rated for 100 tons delivers it. They open the stopper. Metal flows into the pouring basin. Orange-white. Brightness hits 10,000 candelas per square meter. Don't look without protection. Pour rates 110 pounds per second. Pouring 15 tons takes 5 minutes. Can't stop. If you do, the metal freezes unevenly. You get cold joints, cold cracks, internal stresses. The blocks scrap. Metal fills the mold from bottom to top. Forces air out through ventilation channels 3/4 of an inch across. The pour's continuous. Mold's full. They pull the ladle back. Metal cools. Cooling 3 weeks, 21 days, 504 hours. Can't rush it, otherwise thermal stress, micro cracks, uneven structure. Outside looks fine, under load the stresses surface, block cracks. They install 12 temperature sensors, monitor the gradient. Difference between center and surface no more than 90 degrees Fahrenheit. First day temperature drops from 2400 to 1470. Rate 36 degrees per hour. Second day from 1470 to 930. Rate 22 degrees per hour. After a week, 212 degrees. After 3 weeks, room temperature, 72 degrees. They break the mold. Sand falls away. Clean it with shot blasting. Steel shot diameter 0.04 inches. Pressure 87 psi. Shot velocity 230 feet per second. Cleaning 2 hours. Removes sand, scale, flash. Surface clean. Machining. Block on a CNC gantry mill. Work envelope 16 by 10 by 6.5 feet. Milling the datum surfaces. Bottom plane is the reference. Cutter 16 inches in diameter. running at 300 revolutions per minute. Feed rate, 20 inches per minute. Depth of cut, 0.2 inches, removing 1.25 inches of stock. Flatness, plus or minus 0.002 inches per foot. Check it with a laser level. Boring the cylinder holes. 16 cylinders in a V at 45 degrees. Diameter, 11 inches. Tolerance, plus 0.0008, minus 0. Boring head set to 11.02 inches. Cutting speed, 400 feet per minute. Feed point 004 inches per revolution. Depth, 0.008 inches per pass. Final diameter, 11.008 inches. Surface finish, 63 microinches. One micrometer, 1/1000th of a millimeter. A human hair is 70 micrometers. The tolerance on the cylinder is 35 times thinner than a hair. The piston moves at 1,000 RPM. The clearance between piston and cylinder is 0.1 millimeter. More, gases blow by, compression drops, the engine loses power, burns oil. Less, the piston seizes. One correct value, deviation is not allowed. Every cylinder is measured with a bore gauge, 3-point, accuracy 0.001 millimeter. 3 sections along the height, 4 positions around the circumference, 12 measurements per cylinder. Shop temperature is 20 degrees plus or minus 1. Humidity 50%. Metal expands. 1 degree changes the dimension by 0.012 millimeters. Climate control is mandatory. They machine the crankshaft bearing surfaces, diameter 150 millimeters. Tolerance plus or minus 0.015. Holes for the camshaft, mating surfaces for the heads. Full cycle, 4 weeks. 28 days, 672 hours of machine time. A block weighing 55 tons, 13 feet long, 16 perfect cylinders, miles of internal passages, tolerances in micrometers. Ships to assembly. They install a 7,000-pound crankshaft, 16 pistons at 44 pounds each, cylinder heads, turbocharger, fuel injection system. 3 months later, the engine's ready. 4,500 horsepower, 15,000 pound-feet of torque, bolted to a locomotive. That locomotive pulls 120 cars, 11 million pounds of cargo, 60 miles per hour, through the Colorado mountains, across the Nevada desert, non-stop for years, for decades. And it all started with sand and a ladle of molten iron. That's how they make locomotive engine blocks, from casting to micrometric precision. If you're interested, hit like, drop a comment with engines you know, subscribe. We show you how giants are made.
Picture a metal lighter than plastic, burns brighter than the sun itself, and you can pull it straight from seawater. Sound like science fiction? This is magnesium, the metal that revolutionized aviation, space exploration, and even your smartphone. Every year, humanity produces over 1,200,000 tons of this remarkable material. But few people know that behind an ordinary chunk of silvery metal lies technology worthy of science fiction. How does material stronger than steel and lighter than aluminum emerge from ordinary seawater or rock? You'll discover why magnesium burns at temperatures reaching 3,000 degrees, how it's extracted from the ocean floor, and why no modern aircraft can exist without it. Watch until the end. The finale will transform your understanding of what lightness and strength really mean. This is the story of the metal of the future, already here. The story of magnesium began in 1788 in a small English town called Epsom. A local farmer named Henry Wicker noticed something odd. His cows refused to drink water from a particular well. The water was bitter, but it had an amazing property. It healed. People from all around started coming to this spring. That's how a mineral was discovered, later named Epsom salt or magnesia. But this was just the beginning. Pure metallic magnesium was first produced by British chemist Humphrey Davy in 1808 through electrolysis. He passed an electric current through molten magnesium salt and got silvery drops of a previously unknown metal. The metal turned out to be remarkable. It was incredibly light yet strong, and most astonishing, it burned with a blinding white flame, brighter than any material known at the time. In the 19th century, magnesium was rarer than gold. Scientists produced it by the gram in laboratories for experiments. Everything changed when inventors realized something. Magnesium could create brilliant light. Early photographers fell in love with this metal. A flash of magnesium powder delivered such powerful light that you could take pictures even in total darkness. Picture this. The 19th century, a dark studio. A photographer ignites a pinch of magnesium powder and boom! A blinding flash illuminates everything around. That's exactly where the expression magnesium flash came from. But the real breakthrough happened in the 20th century when humanity mastered mass production. Magnesium turned out to be the ideal material for aviation. Lightweight, strong, easy to machine. During World War II, magnesium production skyrocketed tenfold. Military aircraft needed lightweight and durable parts, and magnesium became a strategic material on par with oil and steel. But where does this amazing metal come from? Magnesium is one of the most abundant elements on Earth. It's the 8th most common in the Earth's crust. But you won't find it in pure form. It's too chemically active and always bonded with other elements. The main sources of magnesium are dolomite and magnesite, rocks extracted through open-pit mining. The largest deposits are in China, Russia, Turkey, and North Korea. But there's another source, practically inexhaustible: the ocean. Every cubic mile of seawater contains about 3 million tons of magnesium. Imagine the scale. The world's oceans hold roughly 4 quadrillion tons of magnesium. That's enough to last thousands of years even at current consumption rates. That's exactly why many modern plants are built right on the coast. Why dig in the ground when you can draw from the ocean? Now let's dive into the actual production. There are 2 main methods for obtaining magnesium: thermal and electrolytic. Let's start with the thermal method, which is used when the raw material is dolomite or magnesite from quarries. First, the rock is crushed into small pieces, no bigger than a walnut. Then these pieces go into huge rotating kilns. Picture a steel cylinder the length of a football field, slowly turning. Inside, temperatures hit over 1800 degrees Fahrenheit. At that temperature, carbon dioxide burns off from the dolomite, leaving magnesium oxide, a white powder that looks like chalk. This powder gets mixed with coke and silicon, then pressed into brick-sized briquettes. These briquettes are loaded into special retorts, sealed steel vessels that can withstand extreme conditions. That's where things get really interesting. The retorts are placed into massive furnaces and heated to 2,200 degrees Fahrenheit. At this temperature, the chemical reaction begins. Silicon displaces magnesium from its compounds. But there's a problem. At this temperature, magnesium turns into vapor. Yeah, you heard that right. The metal evaporates, just like water in a kettle. The magnesium vapor rises up through the retort and enters a condenser, a specially cooled chamber. Here, the temperature drops sharply and the magnesium vapor condenses. Crystals of pure metallic magnesium grow on the cold walls. It's like frost on a window, except instead of ice, it's silvery metal. The process happens in a vacuum or in an inert gas atmosphere, Because magnesium is so reactive, it can ignite even in regular air at high temperatures. After several hours, they open the retort. Inside, an ingot of pure magnesium weighing about 22 pounds. It's warm, silvery, covered with a thin oxide film. Now let's break down the electrolytic method. This is exactly what they use when extracting magnesium from seawater. The process starts right on the ocean shore. Seawater gets pumped into massive tanks and treated with lime. The lime reacts with magnesium salts dissolved in the water, forming a white precipitate, magnesium hydroxide. This precipitate settles to the bottom. They collect it and rinse it. You get a white paste that looks like toothpaste. They treat this paste with hydrochloric acid, producing magnesium chloride, a clear solution with a bitter taste. The solution gets evaporated in enormous vats, yielding magnesium chloride crystals, white like coarse salt. These crystals are the key to obtaining pure metal. They load them into electrolytic cells, massive steel containers lined with refractory brick. Inside, molten magnesium chloride at 1300 degrees Fahrenheit glows orange like volcanic lava. A powerful electric current flows through the molten salt, thousands of amps. The magic of electrolysis begins. At the cathode, the negative electrode, droplets of pure magnesium form. They float to the surface because magnesium is lighter than the salt it's extracted from. A layer of liquid metal forms on top, which workers periodically collect with a special ladle. Picture this: a ladle scooping silvery liquid from the surface of a glowing orange melt. It's like skimming cream off milk, except the cream is molten metal at 1200 degrees Fahrenheit. The magnesium is poured into molds and left to cool. You get ingots weighing between 11 and 33 pounds each. They're silvery, lightweight. You can lift a 33-pound ingot with one hand. The surface quickly forms a thin oxide film that protects the metal from further oxidation. Without this film, magnesium would slowly oxidize even in air. Now we've got pure magnesium. But what do we do with it? The applications are vast, and all of them are impressive. Let's start with aviation and aerospace. Magnesium and its alloys are used to make aircraft fuselages, engine components, landing gear. Why? Because weight is everything in aviation. Every pound saved means less fuel and more payload. Magnesium alloys are 40% lighter than aluminum ones with comparable strength. A modern passenger airliner contains several tons of magnesium alloys. Spacecraft and satellites too. When you need to put cargo into orbit, where every pound costs thousands of dollars, magnesium is irreplaceable. The automotive industry has fallen in love with magnesium too. Engine blocks, transmission components, wheel rims, all made from magnesium alloys, especially in sports and racing cars where weight is critical for speed and handling. A single magnesium rim weighs half as much as a steel one with the same strength. Electronics, another massive area where it shines. Laptop cases, tablets, smartphones, cameras, often made from magnesium alloys. Why? Lightweight plus excellent heat dissipation plus strength. Your smartphone or laptop might be packing magnesium right now. Magnesium is also used to protect other metals from corrosion, so-called sacrificial anodes. They're installed on ship hulls, underwater pipelines, oil rigs. Magnesium oxidizes first, protecting the main steel structure. Global magnesium production sits at around 1.2 million tons per year. China cranks out about 85% of all magnesium. Russia, the US, and Israel, other major producers. Magnesium prices swing from $2,000 to $4,000 per ton, depending on purity and market conditions. That's cheaper than aluminum, but pricier than steel. And so, traveling from bitter water in an English well, through dolomite quarries and endless oceans, through the hellish heat of furnaces at 1200 degrees, and the cold of crystallization, magnesium emerges into the world. A metal lighter than plastic and stronger than many steels. This is the story of how humanity learned to transform rock and seawater into a material that lifts planes into the sky and sends satellites to the stars. Every time you board an aircraft, hold your smartphone or watch fireworks burning with blinding white flame. Remember, behind it all is magnesium, an ancient element we learned to tame just 200 years ago. A metal that taught us lightness and strength can go hand in hand. The metal of the future harvested from an infinite ocean that will serve humanity for thousands of years to come.
Your smartphone would weigh over 2 pounds and be an inch thick. A can of Coke would cost $5. A Boeing 747 couldn't cross the Atlantic. It'd run out of fuel halfway. And half the stuff in your house simply wouldn't exist. All because of one metal that humans didn't discover until 1828 and couldn't mass produce until 1886. Before that, the world ran on iron, steel, copper, and bronze, metals too heavy, too expensive, or too weak for modern life. Today, we're heading inside an aluminum plant, and I'll show you what properties emerge at each stage. This aluminum plant sits right on the riverbank. That's no accident. It's been running non-stop for over 120 years. It's here because it has direct access to massive hydroelectric power. That's critical because making aluminum takes more electricity than almost any other industrial process on Earth. Walk onto the grounds and the first thing you feel, a low hum from the transformers. The smell of superheated metal hangs in the air constantly. The plant never stops, not for a minute. The raw material is bauxite, a reddish-brown powder that arrives on ships from tropical countries, Jamaica, Australia, Guinea. If aluminum had never been discovered, we'd still be mining iron ore for everything. Steel production needs coal. It gives off massive emissions. Aluminum here, it runs on clean hydropower. Without aluminum, global carbon emissions would be roughly 15% higher from metal production alone. The first stage is processing bauxite through the Bayer process. The ore is crushed and mixed with caustic soda, then heated to 347 degrees Fahrenheit under pressure in autoclaves. Under these conditions, aluminum oxide dissolves while iron and silicon remain as red mud, a thick, bright, rust-colored mass that's diverted to special storage facilities. The output? Pure white aluminum oxide powder, also known as alumina. To produce 1 ton of alumina, you need to process about 2 tons of bauxite. This is where aluminum's first critical property is established: incredible corrosion resistance. In air, aluminum instantly forms an ultra-thin oxide film that locks the metal into protection against further oxidation. If we use steel, every outdoor structure would need constant repainting. Steel ships require dry dock and repainting every few years. Aluminum boats serve for decades without maintenance. Without this property, coastal cities would burn billions on infrastructure upkeep. The alumina is moved to the electrolysis hall, and this place is impressive. A massive room with rows of reduction cells radiating waves of heat. These are glowing rectangular pools about 15 feet long, filled with molten cryolite at a temperature of around 1700 degrees Fahrenheit. The surface of the cells flickers orange, and the air shimmers from the heat. The alumina dissolves in this bath. Then, a current of 150,000 amps is run through each cell, enough electricity to power 15,000 homes. The current rips aluminum atoms away from oxygen atoms. Pure molten aluminum sinks to the bottom. Oxygen rises to the top. This is the Hall-Héroult process, invented in 1886, and it's still the only economically viable way to produce aluminum. Before it, aluminum cost more than gold. Napoleon III used aluminum plates for his most important guests, while everyone else ate from gold ones. Without the Hall-Héroult process, aluminum would cost hundreds of dollars per pound today, and a can of soda would set you back a fortune. After a full day of operation, the molten aluminum gets pumped out and poured into crucibles, 10 tons each. The liquid metal glows with a soft, silvery light, nothing like orange cast iron or golden bronze. This shimmering metal demonstrates aluminum's most critical property, strength-to-weight ratio. Aluminum's 3 times lighter than steel, but with the right alloying, nearly as strong. A Boeing 747 made of steel would weigh 1,200 tons instead of 400. You'd need engines 3 times more powerful, burning 3 times more fuel. But carrying that extra fuel adds weight, which demands even more fuel. The tyranny of the rocket equation makes long-haul flights impossible. Without aluminum, commercial aviation as we know it doesn't exist. Short flights on steel planes? Possible. But New York to London would need 2 refueling stops, turning 8 hours into 20, while ticket prices would shoot up to several $1,000s. Molten aluminum gets poured into molds, forming ingots weighing several tons. Then they're reheated to 850 degrees Fahrenheit and pass through massive rolling mills. The rollers press down with thousands of tons of force, and with each pass, the ingot gets thinner and longer, transforming into sheets ranging from 0.02 of an inch to several inches thick. Rolling aligns the grain structure, locking in specific mechanical properties. Here's where another critical quality emerges: electrical conductivity. Aluminum conducts electricity 60% as well as copper, but weighs only 30% as much. Every high-voltage power line uses aluminum around a steel core. The aluminum conducts the current while the steel carries the load. If we had to use copper instead, the wires would be 3 times heavier, the support towers would need to be 3 times stronger, and spaced closer together. Building power grids would cost 4 times more. Rural electrification would never have happened, and your monthly electric bill would triple. Every sheet undergoes the strictest quality control, and there's a concrete reason for that. On April 28, 1988, Aloha Airlines Flight 243 was cruising at about 24,000 feet above Hawaii when passengers heard explosive decompression. The entire upper section of the forward fuselage tore away, exposing nearly 18 feet of skin and opening the cabin to the sky. 1 flight attendant was killed, 65 passengers injured. The investigation revealed that the aluminum fuselage had developed microscopic fatigue cracks after years of pressurization cycles. With every takeoff, the fuselage expands under pressure. With every landing, it contracts. Thousands of these cycles, and invisible defects appear in the metal. Tiny cracks grew and connected until the structure failed catastrophically. The aircraft had completed 89,000 flight cycles, and technicians couldn't detect such small defects. This tragedy completely transformed how the aerospace industry inspects aluminum. Today, every single sheet goes through eddy current testing, which detects surface cracks as small as 0.004 of an inch deep, ultrasonic testing that finds internal defects, and X-ray examination for critical components. Plus fatigue testing. Samples get bent millions of times, simulating decades of flight cycles to verify the alloy's reliability. The rejection rate for aerospace aluminum is 12%. Every 8th sheet fails inspection and gets sent back for remelting. That number seems high, but after the Aloha disaster, the industry decided, better to lose metal than lives. Aluminum that passes inspection goes to manufacturers, who turn it into everything, from aircraft to soda cans. A major plant produces around 300,000 tons annually. And virtually all that rejected metal doesn't go to waste. Aluminum can be remelted infinite times without losing its properties, and remelting takes just 5% of the energy needed for primary production. Without aluminum, cans would be made of tin-plated steel, weighing 3 times as much. A 12-pack of Coke, 24 pounds instead of 9. Shipping costs triple, prices double. Construction would look completely different. Modern curtain walls use aluminum frames, strong enough for glass but light enough that buildings don't need massive reinforcement. Without aluminum, tiny windows in thick walls, or steel frames so heavy that buildings over 50 stories become impractical. Modern glass skyscrapers don't exist. Computers and smartphones would be different too. That aluminum laptop body would have to be plastic or magnesium. Plastic isn't rigid enough and cracks. Magnesium is light but catches fire during machining. The plant's been running for over 120 years, producing roughly 20 million tons of aluminum, turned into planes, cars, buildings, power lines, packaging, and electronics. Without the electrolysis process running in those reduction cells, none of this exists. We'd be trapped in a world that's heavier, more expensive, and far more limited.
And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you. Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture. Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast. To turn a bare base into waterproofing material, The roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness.
The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat-resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance.
After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat. Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Bushveld new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
Every year, humanity throws away more than 50 billion batteries. That's enough to build a tower all the way to the moon. Mountains of toxic metal and chemicals that could become raw material for new life, instead of poisoning the planet. But what happens next to all these power sources? Where do they end up after the charge dies in your phone, laptop, or electric car? Behind the plain doors of an ordinary collection point hides an entire industry of the future. This is a world of giant shredders that grind metal into dust, magnetic separators that sort the invisible, and furnaces reaching temperatures of 3,000 degrees Fahrenheit, hotter than the mouth of a volcano. And here's the best part. By the end of this video, you'll find out what actually happens to the lithium that once lived inside your battery, and why this process is called urban mining for 21st century treasures.
The path to rebirth doesn't start at the factory, it starts in our hands. Collecting used batteries is a massive logistical operation spanning the entire country. Regular people drop off tiny batteries from phones and laptops into special bins installed at electronics stores and supermarkets. Auto shops, like hospitals for cars, pull out massive battery packs from electric vehicles, hundreds of pounds each. Industrial facilities running heavy machinery turn in their spent power sources by the ton. It's like thousands of streams flowing into one big river. Old batteries from factories and auto shops get hauled in armored trucks to regional collection centers. Here's what's interesting. Modern smart collection containers have sensors that track fill levels in real time. When a container's almost full, it automatically sends a signal to the logistics company, which plans a pickup route.
When mountains of collected batteries arrive at the sorting facility, one of the most complex and critical stages begins. Batteries come in dozens of different types: lithium-ion, like the one in your smartphone, nickel metal hydride from old toys, lead acid from cars. Mixing them during recycling is like mixing sand with sugar. At small collection centers, workers sort batteries by hand, like jewelers, relying on markings and appearance. But at large-scale facilities, technology takes over. Batteries move along conveyor belts under the watch of artificial intelligence. Computer vision systems equipped with X-ray and spectroscopic scanners identify the chemical composition of each battery in fractions of a second. Robotic arms snatch the right types from the stream at lightning speed and sort them into different containers. Despite automation, human oversight remains irreplaceable. Operators, like air traffic controllers, monitor the machines and step in when things get complicated. If a battery has a damaged casing or missing labels, only a human can make the right call. This is especially true for the massive batteries from electric vehicles. These giant blocks, weighing up to half a ton, are dismantled into smaller modules using specialized robots, but the final cell sorting is often done by hand. It's painstaking and dangerous work that demands total focus. At the end of the day, every properly sorted battery isn't just a piece of metal. It's a chance to return the most valuable rare earth elements, like cobalt and lithium, back into the economy, and to reduce the enormous damage caused by mining them in the first place. After sorting, the batteries head to their execution.
the shredding floor. They fall into the steel jaws of a giant shredder. This is a true industrial monster, whose hardened steel blades can grind up even the armored casing of an electric vehicle battery. Inside the protected chamber, total metallic chaos unfolds. Deafening roars, grinding, and cracking. Batteries literally torn into tiny pieces. But this process is extremely dangerous. Any energy left in a battery can lead to fire or explosion. To prevent this, engineers developed several brilliant solutions. Before shredding, batteries are often subjected to cryogenic freezing in liquid nitrogen at temperatures of -320 degrees Fahrenheit. This not only makes the metals more brittle, but also completely neutralizes any chemical activity. Some shredders operate in sealed chambers filled with inert gases to eliminate contact with oxygen.
The shredded pieces pass through a system of magnetic separators that pull steel, nickel, and cobalt from the stream with incredible precision. But the most valuable thing is the fine black powder that settles in specialized dust collectors. It's known as black mass. Right here in this unremarkable-looking dust lie the real treasures of the 21st century: lithium, cobalt, manganese, and graphite. Plastic residue and traces of electrolytes get washed away with special solutions. Engineers in armored control rooms monitor the process through thick glass, controlling temperature and pressure. If a battery does explode, the system instantly snuffs out the flash, and the process doesn't stop for a second. Once the precious black mass has been extracted from the chaos of shredded batteries, the real alchemy begins. Metals that seemed forever locked inside old batteries are recovered using two main methods: hydrometallurgy and pyrometallurgy. Hydrometallurgy is a process similar to cooking up a complex chemical soup. The black mass is plunged into massive reactors filled with acid solutions, typically sulfuric or hydrochloric acid. With constant stirring and heating, metals, lithium, cobalt, nickel, literally dissolve, transitioning into liquid form. To extract a specific metal from this soup, an ion extraction process is used. Special reagents are added to the solution that selectively bind to only one metal, like a key to a lock. As a result, each metal settles into a separate layer. If hydrometallurgy is delicate chemistry, then pyrometallurgy is the primal force of fire. Here, everything literally burns and melts. The black mass gets loaded into a massive arc furnace, where temperatures reach nearly 3,000 degrees Fahrenheit. At that kind of heat, metals melt, and plastic and other organic remnants simply burn away. The molten mass separates under gravity, like oil and water. Heavier metals, such as cobalt, nickel, and copper, sink to the bottom, forming a valuable alloy. The lighter lithium stays in the top layer, in what's called slag. Then this slag is extracted and processed separately to obtain pure lithium. This method is faster and handles larger volumes, but it's also more energy intensive.
After cooling, the extracted metals emerge as the purest ingots, shiny, smooth, and ready for their second life. Cooling after the pyrometallurgical process is just as critical a stage. If you simply let molten metals cool in open air, it can take several days and lead to uneven crystal structure formation, which degrades quality. That's why cooling is always controlled. Ingots might move slowly along a conveyor beneath powerful fans. It's like a giant hairdryer that quickly yet evenly cools the surface. For an even faster process, red-hot ingots can be plunged into massive tanks of water or special cooling fluids. It's an incredible sight, glowing metal hitting water instantly shrouded in clouds of hissing steam.
Sometimes they use combined cooling too, air cooling first, then water cooling, to reduce internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse, especially in manufacturing new high-tech batteries. The recovered lithium, now in the form of ultra-pure lithium carbonate, heads back to factories to become the heart of new batteries that'll power electric cars or even your phones. Nickel can become part of super strong alloys for turbines that generate energy from wind, and cobalt becomes an irreplaceable component in complex medical equipment. We're literally closing the loop. Old, discarded batteries give life to new, cutting-edge technologies.
Tossed batteries, they can become a full-blown environmental disaster. First, they're packed with toxic heavy metals that seep into landfills, contaminate soil, poison groundwater, and wreck everything around them. Second, mining new rare earth metals is an incredibly dirty, destructive process that drains natural resources and devastates ecosystems on a massive scale. Recycling tackles both problems at once. And here's the real power move. The more batteries we recycle, the less we depend on unstable raw material supplies from other countries, strengthening our technological independence. Despite lithium's critical importance, only about 1% of this metal gets recycled globally today. The main reason? High costs and complex processes. But right now, researchers around the world are developing new, cheaper technologies that could dramatically change the game in the coming years.
Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. but installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast's force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture. Every year, millions of components, tons of alloys, and hours of high-precision calculations come together in one deadly symphony. This missile isn't simply metal. It's a moving brain, an engine, and coded death that flies over 1,000 miles whilst hiding from radars. How is a secret capable of changing the course of battle born from hundreds of metal sections? Stay until the end. I'll reveal one production secret that few people know. Want to know what's hidden inside? Imagine lasers, press forming, robots welding components in clean rooms with tolerances of 1/100th of a millimeter. All of this for a single flight. Designing the Tomahawk missile is a symphony of formulae and calculations. Engineers don't simply draw a body. They solve equations that must allow it to cut through air with centimeter precision. Every surface and curve is calculated in computer-aided design systems and undergoes aerodynamic modeling. The goal is to create a body that will fly over 1,000 miles, remaining almost invisible and stable at an altitude of 100 feet or 160 feet above ground. In digital simulations, they test wind force, resistance at speeds of 550 miles per hour, and the effects of rain. One mistake, and instead of a precise strike, the missile will hit a barn on the outskirts. Body components, electronics, payload, all of this fits into nearly 20 feet of length and 20 inches in diameter. It's genuine artistry, packaging death with such elegance. Only after dozens of virtual tests does the missile move to the production phase. After the calculation stage, drawings are transferred to the real world, to factories with high-precision equipment. Here, not a single crack nor an extra micron can be permitted. The missile body, over 18 feet long, is assembled from sections manufactured from high-quality aluminum alloys, sometimes with titanium added. This is an aerodynamically refined cylinder that must withstand overloads, vibration, and temperature fluctuations. Blanks are cut with laser or water jet installations with tolerances up to 1/100th of a millimeter. Then press forming. Large hydraulic machines bend metal like fabric. Welding is conducted in an inert atmosphere, often by robotic arms, to avoid even the smallest oxygen inclusions. Technologists check welds hourly with ultrasound and apply special anti-corrosion coatings. Even the inscription Tomahawk isn't applied as decoration, but as a marker of version and the missile's history. For the cruise missile, a compact Williams F-107 turbofan engine is used, similar to a small aircraft engine but adapted for high maneuverability. Turbine blades are manufactured from nickel alloys in a form resembling sculpture more than a technical component. They're cast using precision casting methods, then polished to mirror finish to give air minimal resistance. The compressor and combustion chamber are a complex mosaic of dozens of elements. Each component is checked for seal integrity because any micro leak and the missile simply won't launch. The nozzle is manufactured from heat-resistant alloy capable of withstanding flame temperature without deformation. Engine assembly occurs in clean zones similar to laboratories. Workers in sterile suits, stable temperature and humidity. After assembly, each engine undergoes individual ignition testing in a test chamber. The engine simulates genuine flight, but not in the sky, on a concrete table with sensors. Tests last for hours. They check stability of revolutions, temperature, fuel consumption, and even noise, because volume could betray the missile's position. And only when the engine has sung its song is it integrated into the Tomahawk's body, as though breathing life into it. When the body is ready and the engine installed, the missile still isn't ready to fly. It knows nothing yet. It must be taught. Inside is a genuine brain, a node of microprocessors, sensors, antenna, and memory blocks. But the moment it receives its first power signal, a machine consciousness awakens within it. Its navigation is an entire ensemble of systems. Inertial sensors maintain course even if the signal disappears. GPS correction helps prevent deviation from the route. But most important is its ability to see. Special cameras analyze terrain, comparing every hill or bridge with the map stored in memory. If there's forest beneath it when there should be field, it knows something's wrong. It makes decisions. The control system works like nervous tissue, flexible and infallible. Small stabilizers and control surfaces respond to every tilt and altitude change. And finally, the most important thing, that which transforms the missile from an engineering creation into a weapon, its warhead. It looks simple, a cylinder hidden in the body. But inside is explosive capable of penetrating concrete and destroying equipment. It's manufactured separately under conditions of absolute sterility. Not a single spark. This is work where mistakes aren't corrected, they're not permitted. Before final assembly, each component undergoes inspection, X-ray, vibration tests, electronic diagnostics, and then assembly. Quietly, step by step, as though someone's assembling not a weapon but an antique clock that must strike just once. And when everything's connected, the missile silently settles into its container. It doesn't glow, doesn't flash, it simply waits. Its flight lies ahead, but it's already ready.
Picture this. 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads. The first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal in blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green.
The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost.
Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math. Around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution. And it started in cold Sweden, in the city of Luleå, above the Arctic Circle. 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen. Pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks. The first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy? It's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills. All of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant, capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry, and remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2,000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane, 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit two Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and De Hard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber, layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound, works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust, 320 kilonewtons, 72,000 pounds of force. Fan diameter, 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque, 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. Minus 22 in Sweden, plus 113 in Spain. Everything works. November 13, 2019. Type certificate. The Beluga cleared for flight. January 9, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed.
Every year in the world, only 21 mysterious B-2 Spirit aircraft are created, genuine ghosts of the sky. Its length is almost that of a multi-story building, whilst its wingspan is greater than a football pitch. But the main intrigue lies in the materials. Composites, titanium, and aluminium alloys make it lightweight, yet incredibly strong and almost invisible to radars. Radio waves become lost in the layers. Paint absorbs signals, and engines hide their thermal signature like a shadow in the night sky. This isn't simply an aircraft, it's an engineering myth about which legends have circulated for decades. Watch until the end, and you'll learn a secret not shown even in military archives. Everything begins with material selection, and here the B-2 Spirit is truly extraordinary. For its body, they don't use ordinary metal as in old aircraft, but take composites, titanium, and aluminium alloys. Composites are multi-layered sandwiches of fibers and resins that are lighter than steel yet significantly stronger. It's precisely thanks to these materials that the aircraft not only withstands colossal loads, but also remains almost invisible to radars. Radio waves simply become lost in the composite layers without reflecting back. Imagine, the B-2's length is almost 69 feet, whilst its wingspan exceeds 171 feet. It's like a football pitch, only instead of grass, there's black stealth gliding across the sky. The empty weight of the B-2 is over 71 tons, whilst maximum takeoff mass reaches 171,000 kilograms. But even with such dimensions, it appears elegant because its shape is pure aerodynamics. No superfluous protrusions, everything smooth as in nature. Every detail is manufactured with jeweler's precision. Titanium and aluminium are used where special strength is needed, for instance in engine mounting points or undercarriage. And composites cover nearly the entire surface. They're responsible for stealth and lightness. Incidentally, special body coating not only absorbs radio waves, but protects the aircraft from extreme temperatures at altitudes exceeding 50,000 feet. Next follows multi-stage processing, grinding, quality control, application of special layers. Every millimeter is checked with laser scanners, so there's not a crack nor the slightest gap. Here, everything is at high technology level. Robots and people work together, creating a genuine work of engineering art. It's precisely thanks to these materials and technologies that the B-2 Spirit can fly thousands of miles, remaining invisible both to radars and thermal imagers. In the B-2 Spirit, nothing is accidental. Every curve of the fuselage, every wing line is the result of thousands of hours of calculations and tests. Engineers literally draw the aircraft in air so that it doesn't simply fly, but merges with the sky. It's precisely thanks to this shape that the B-2 looks so futuristic. It's as though created not to challenge the air, but to become part of it. Every detail, even the slightest protrusion, is calculated on supercomputers. Imagine, even rivets and joints on the body are hidden so as not to create unnecessary reflections for radars. And there's also a secret weapon here: special paint. This isn't simply a black matte layer, but a multi-component coating that absorbs radio waves and doesn't allow them to reflect back. That's precisely why even powerful radars see the B-2 as a tiny dot or don't notice it at all in the sky. Assembly of the B-2 Spirit is a genuine engineering performance that occurs in enormous workshops accessible only to chosen few. Here reigns an atmosphere of maximum secrecy. People and robots work together like a single team. Robots lift and hold massive sections whilst engineers manually install the tiniest details. The aircraft body is assembled piece by piece like a gigantic three-dimensional puzzle, where every element must fit perfectly in its place. All joints are checked with lasers. This looks like a scene from a science fiction film. Enormous cranes, laser scanners, people in special clothing, robots moving with incredible precision. Every day in these workshops is another step towards creating an aircraft that changes the rules of the game in the aviation world. Next, engines enter the stage, the genuine heart of the B-2 Spirit. Designers hide engines inside the body rather than placing them outside as in most aircraft. Thanks to such integration, the B-2 appears maximally smooth, and this also helps hide thermal traces. The whole trick is in the exhausts. Hot gases that are usually clearly visible to infrared sensors here pass through special long channels. In these channels, gases cool, mix with cold air, and only afterwards exit outside. Therefore, even modern thermal imagers see the B-2 as a barely noticeable shadow in the sky. The aircraft cockpit is isolated, protected from noise and light, comfortable even during many-hour flights. Next, onto this foundation are applied layers of insulation so that inside it's always quiet and comfortable even if engines roar outside. The feeling is as though you're in a capsule that screens you from the entire world. Now, in the cockpit center are installed two seats. They stand side by side like in a modern sports car. Seats are soft but strong with numerous adjustments. Before is an enormous digital screen. All controls are to hand. Touchscreen panels, joysticks, buttons with different textures so they're easy to find even by touch. Around are panels with instruments. They don't protrude but smoothly transition one into another like waves. A folding rest area, a folding bed, space for food, even a small toilet. This is space where one can relax whilst one's partner holds the controls. Everything is made so that crew can remain focused and not tire even during flights lasting over a day. When the cockpit is ready, it's covered with special coating that protects from temperature fluctuations, from bitter frosts to heat. All joints are sealed so there's not a single draft or extraneous noise.
Have you ever seen what molten bronze looks like? I have. It's golden, almost like the sun, and flows slower than water, thick, heavy, with this inner weightiness to it. And when 70 tons of this metal get poured into a single mold all at once, it's a sight you can't look away from. Today we're at a factory that makes propellers for military ships. This is one of those places they don't run tours through and almost never film inside. And I'm going to show you the entire journey from molten bronze to a polished giant that will silently push thousands of tons of steel through the ocean. Let's start with a question I asked myself when I got here. Why bronze? A warship is a steel machine. Steel hull, steel superstructure, steel weapons. So why make the propeller from a different material? The answer is simple yet profound. Steel rusts in seawater. The propeller is constantly submerged, constantly spinning, constantly in contact with an aggressive environment. A steel propeller would turn into a rusty hedgehog in just a few years, one that can't do its job anymore. That's why they use nickel aluminum bronze here, an alloy that sailors and metallurgists call nibral for short. Nibral is a mix of copper, aluminum, nickel, and iron in precisely calibrated proportions. Copper provides the base and corrosion resistance. Aluminum strengthens the alloy and reduces weight. Nickel adds hardness and erosion resistance, and iron refines the grain structure, making the metal uniform. Every element here is deliberate, the result of decades of research and real-world testing. Nibral doesn't rust, resists erosion incredibly well, and has enough strength to handle the loads from spinning at full speed underwater. Now, about scale. A propeller for a destroyer or nuclear submarine, this isn't something you can pick up with your hands. The diameter of such a propeller reaches 20 feet or more, and each blade is comparable in size to a small car. The weight of the finished product, dozens of tons. And it all starts with 70 tons of liquid bronze that needs to be poured into a single mold in one continuous process. 70 tons. That's roughly the weight of 12 fully loaded pickup trucks. And all this massive metal at a temperature of around 2,000 degrees Fahrenheit has to get into the mold evenly, no pauses, no stops. The metal is melted in large induction or arc furnaces. Depending on the plant's configuration, there might be several of these furnaces, and they run in parallel to accumulate the necessary volume of molten metal by the time of pouring. When the metal hits the right temperature, lab techs take a sample, a small portion of the melt, and send it for rapid chemical analysis. If the element ratios check out, they greenlight the pour. If something's off, they adjust it right there in the furnace, adding whatever element is needed, then take another sample. The pour happens from a big ladle suspended from an overhead crane. They tilt the ladle, and metal starts flowing into the gating system of the mold. It looks like this, a thick golden stream with bright glow and a cloud of steam rising up. The air shimmers from the heat, and 30 feet away you can feel the hot wave hit your face. The foundry workers stand off to the side in protective suits and shields. Even several yards out, the heat hits your whole body. They control pour temperature by adjusting the ladle tilt. Too fast, and the metal churns turbulently in the mold, trapping air and creating voids. Too slow, and the first portion starts solidifying before the mold fills, leaving internal seams in the casting. So the pace stays steady, continuous, dialed in by experience. When the mold is complete, they leave what's called a riser at the top, an extra reservoir of metal that feeds the casting as it shrinks during cooling. Without it, shrinkage cavities form inside the propeller, voids that would render the blade useless. The riser gets cut off later, but during the pour, it's a critical part of the process. The mold for a propeller is a massive structure that takes up a significant portion of the foundry floor. It's assembled over weeks from special molding sand reinforced with binding resins. Each blade has its own complex geometry, twisted, uneven, with a precisely calculated profile. This geometry is built into the sand mold with high precision. The raw casting already needs to be very close to the final part. Worth noting separately are the cores. Cavities are designed inside the blades to reduce weight without sacrificing strength. To form them, sand cores are mounted in the mold on metal supports called chaplets. During the pour, the chaplets fuse with the base metal and become part of it, while the cores are later knocked out of the finished casting. Sounds simple, but in practice, it's precision work, carefully controlling the position of every rod. If a rod shifts under the weight of molten metal during the pour, the blade wall comes out uneven. An uneven wall means imbalance. Imbalance on a submarine propeller means vibration. Vibration means noise. And noise underwater? That's a death sentence for a sub, because enemy hydrophones will pick it up. This brings us to the main theme of this facility: silence. A warship, and especially a submarine, must be as quiet as possible. The propeller is the primary source of underwater noise. There are two mechanisms: mechanical noise from imbalance and vibration, and cavitation noise. Cavitation is a phenomenon where microscopic vapor bubbles form on the blade surface due to pressure differences, then collapse with a distinctive crackle. Each pop is a micro-impact that, over time, destroys even bronze, leaving small pits on the surface. But the main problem isn't wear, it's sound. That crackling travels brilliantly through water and is easily detected by sonar systems. That's why blade surfaces must be perfect: no roughness, no waviness, no deviations from the calculated profile. That's exactly why there's a 5-axis CNC milling machine standing here. If you've never seen one of these machines, picture something between an industrial robot and a building. The work envelope can handle parts up to 20 feet in diameter. The spindle and cutter move simultaneously along 5 axes, 3 linear and 2 rotational. This lets the tool approach any point on a complexly twisted blade at exactly the right angle and remove metal with micron-level precision. The price tag on one of these machines? A small fortune. But without it, achieving the required surface quality on parts this size is simply impossible. Machining a single propeller takes several weeks. Weeks, not hours. The machine strips away chips continuously, layer by layer, closing in on the final profile. Bronze shavings curl into golden spirals and drop into the catch pan, while beneath the cutter emerges a surface smooth as glass. Operators regularly pause the process to measure blade geometry using specialized probes and laser scanners. Any deviation from the theoretical profile? The program gets adjusted. The goal is to achieve a surface that matches the blueprint to within hundredths of a millimeter on a part that's 20 feet across. That's like drawing a perfect room-sized circle without deviating from the line by more than the thickness of a sheet of paper. After machining comes balancing. The propeller gets mounted on a balancing stand and spun. Sensors detect exactly where the imbalance is and how much. Technicians manually remove metal from specific spots, literally just a few grams at a time, until the propeller reaches the required balance level. The process is painstaking. Shave off a tiny bit, measure. Shave again, measure again. Over and over until the sensors show it's within spec. On a civilian ship, this level of precision would be considered excellent. On a military vessel, it's the minimum acceptable standard. The final inspection includes complete measurement of every blade, surface roughness checks, and verification of the metal's chemical composition using samples taken during the melt. Each propeller gets a full documentation package, from the melt's chemical analysis to balancing protocols and laser surface scanning reports. This isn't just paperwork. It's a legal and technical passport for a product that'll go on a warship and serve for decades under the harshest operating conditions. I stood next to a finished propeller before shipping, trying to wrap my head around the fact that I was looking at something that had gone from liquid bronze to this golden, polished giant in just a few months, through the work of dozens of people and one very large machine. Somewhere out in the ocean, this propeller will spin in complete darkness, pushing thousands of tons of steel forward. And it'll do it silently. Because that's exactly what it was built to do.
The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on. The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later: catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s, when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals.
Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources, Russia and South Africa. 70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive, 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1200 degrees. Iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not palladium yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery